So until now, we have looked at exact inference algorithms based on bucket elimination to solve both the MPE as well as MAP tasks. We also looked at branch and bound algorithms for solving both of these tasks. Today, what we are going to do is we are going to look at a new type of algorithm or a new class of algorithms called local search algorithms. So local search is a general class of approximate inference algorithms, and in some circles they're also called as hill climbing algorithms for solving optimization types of problems. Before I describe the basic algorithm, let me define some new terms that we will use to specify the algorithm. The first definition is that of a state, and the second definition is that of the neighborhood function. We define a state in local search as an assignment of values to all the variables of interest. Thus, if you're interested in 10 binary variables, then a state is a 0, 1 vector or a bit vector of size 10. The second definition is that of a neighborhood function. A neighborhood function associates a set of states called neighbors to each state. To manage the computational complexity, and remember we always want our computational complexity to be small, we will insist that we use neighborhood functions, or rather we will select neighborhood functions in such a way that each state has linear, or in the worst case polynomial number of states as its neighbors. As we'll see, this is important because if we don't insist on this, our algorithm will be exponential in the worst case. An example neighborhood function in the following. Given a state S, and if you remember, S is nothing but an assignment of values to the variables of interest, the neighbors of S are those states which differ from S in value assignment to just one variable. So let's say you have 10 variables, then it will have, and each variable takes two values, 0 and 1. Then each state will have 10 neighbors, where a neighbor is formed by flipping a value of exactly one variable in the current state S. Clearly, if we use this particular neighborhood function, then the neighborhood function is linear, right? The size of the set is bounded by O of n, where n is the number of binary variables. Similarly, if we have n variables such that each variable takes d values, then each state will have exactly n times d neighbors. Let me now give you a concrete example of a state and neighborhood. Let us assume that we have a Markov network over 5 binary variables a, b, c, d, e, where each variable takes values from the set 0, 1, right? So all of these variables are binary variable, where 0 stands for false, let's say, and 1 stands for true. Let us say that all variables in the Markov network are the variables of interest for our optimization problem that we are going to solve using local search. Okay? Then each state in the local search algorithm is a 0, 1 assignment to all the 5 variables. An example state is given on the slide and is denoted by S. In this state, A takes the value 0, B takes the value 1, C takes the value 0, D 0, and E is 1. Let us define the neighborhood function as follows, right? And it's the same thing that I talked about in the previous slide. The neighbors of a state S, we will say, are all states which differ from S in value assignment to just one variable. Okay, so we just take one variable and flip it. Okay, and those are going to be our neighbors. So technically, since there are 5 variables here, we will have exactly 5 neighbors because each variable can only take 2 values. Okay. Thus, under this definition of neighborhood function, S has the neighbors that are denoted by S1 through S5 on the slide. In the state S1, which is a neighbor of S, A is flipped from 0 to 1. In S2, B is flipped from 1 to 0, and so on. I will now describe the basic local search algorithm for solving a maximization task. Okay? And remember, we are only focusing on discrete graphical models here as well as discrete optimization problems. Okay? We are not using local search here to solve continuous optimization problems. You may ask, why am I focusing on the maximization task rather than the minimization task, right? So whenever I say a maximization task, I'm talking about an optimization problem in which we want the objective function to be maximized. And whenever I'm talking about minimization task, I'm talking about an optimization problem in which the objective function needs to be minimized. Okay. So recall that MPE and MAP inference tasks are maximization tasks. We assume that given a state S, there is a scoring function called score such that calculating the score of S is computationally feasible. In other words, given a state S, score of S can be computed in polynomial time in the size of the graphical model, or in the general context, if you have an objective function, then score can be computed in time that scales linearly with the number of elements in the objective function. The algorithm, the basic algorithm I should say, for local search operates as follows. We begin with the random state S. Let us call S as our current state. Okay. We also maintain the best solution found so far in a quantity or a variable called best. Then we run the following steps until time runs out. Okay, so you will be given a time bound, and as soon as the time bound exceeds, you will stop the algorithm. In these iterative steps, which are under the until loop, what we do is we find a neighbor S prime of S having the highest score among all neighbors of S. Then we update best if the score of S prime is better than S. Okay? Then we replace the current state S by S prime if the score of S prime is better. What I mean by better is that the score of S prime is higher than S. After time runs out, and when the time bound is exceeded, we return the best solution found so far. Okay, so that's our basic local search algorithm. Unfortunately, this algorithm is rarely used in practice because it suffers from two basic issues. Okay, and I should not use the word basic a lot because I'm talking about the basic local search algorithm, but it suffers from like two issues. Okay, and they are like fairly fundamental. The first issue is that local search can get stuck in a local maxima, which is defined as a state S such that all neighbors of S have smaller score than S. As you can imagine, local maximas are problematic because they can be far in terms of score from the global maximas, which is what we want to reach, right? So if you're given an optimization problem, we don't want to reach a local maxima, we want to reach the so-called global maxima, right? Which is the best possible local maxima. Since the global maxima is nothing but the optimal solution, okay? One analogy you can use here is the following, and I'm coming up with this analogy on the fly, so bear with me, okay? So what we can say is that a local maxima is a small hill and global maxima is the tallest mountain ever, let's say Mount Everest, okay? And you want to reach the top of Mount Everest and not the top of a hill, right? Because that's your goal. Your goal is maximization. You want to be as high as possible. However, since you're performing greedy search, okay, you decide that you will never take a step that goes down in terms of altitude from your current location. Okay? And since you are very, very greedy, what will happen is that because of your greediness, you will get stuck at the top of the hill because all steps are going down in terms of altitude. Okay? And you will never reach the top of Mount Everest. Okay? So that's like one way of looking at global maximas, or sorry, local maximas versus global maximas. A second problem with local search is that it may get stuck in so-called plateaus, right, which are flat regions where the best neighbor of S, and sometimes whenever we take a move to the best neighbor of S, those moves are called as locally optimal move. Okay, so a plateau or a flat region is defined as a region where the neighbor of S has the same score as S. Okay, and you will get stuck in those plateaus and you're not improving your current solution. So because of these two problems, the plateau problem and the local maxima problem, the basic local search algorithm is rarely used in practice. Okay? And so we'll see on the next slide how to improve this algorithm. But before that, now comes my favorite part. Okay? And my favorite part being, since we are computer scientists, let us analyze the computational complexity of local search. I will give you 10 seconds to think about it. And again, since this is an online lecture, I'm going to call these 10 seconds as a minute. Okay? And let me give you the answer now. So let n denote the number of variables. Let each variable take d values. And the number of neighbors of each state equals n times d. Let the complexity of computing the scoring function be t. Then the time complexity of each move in local search is O of n times d times t. You can verify this. Thus, and this is what I want to point out, each local search move is linear in the number of neighbors, okay? And it's also linear in t, where t denotes the time required to compute the score. Now you understand essentially why the need to have a neighboring function that has polynomial computational complexity. Okay? If the neighborhood function does not have a polynomial computational complexity, then the overall complexity of each move will be exponential. Okay? And the algorithm will become impractical. Same applies to the time t required for computing the score. Okay, so computing the score should also be polynomial along with the neighborhood function. Next, I'll describe a popular approach for escaping local maximas and plateaus, and this approach is called the random walk approach. There are many other approaches in literature for escaping local maximas and plateaus, right? The two issues with the basic local search algorithm that we discussed on the previous slide. And these other approaches, I should say, include things such as genetic programming and simulated annealing. However, the random walk approach works quite well in practice as compared to these approaches. And I can verify this because I've used the random walk approach extensively myself. The advanced local search algorithm, which uses random walks, is given on the slide. The algorithm takes as input a probability p, okay, as compared to the previous algorithm which did not take as input a probability p. As before, what we do is we start with a random state, let's call that state S, and set the best state, which is captured in the variable best, to the current state S. Okay? Then we run the following steps until time runs out. Again, this algorithm has a time bound, and this algorithm will keep on moving through states until the time bound has expired. Now, these iterative steps in the repeat until loop are the steps where this algorithm differs or deviates from the basic local search algorithm. Unlike the basic algorithm, instead of making a locally optimal move, okay, or instead of always making a locally optimal move, namely what we do is we move from state S to another state S prime having the highest score, where S prime is a neighbor of S. In the advanced algorithm, or which uses random walk, we only make a locally optimal move with some probability. Specifically, if you look at the algorithm, with probability P, we make a random walk move, namely we move to a random neighbor of S. And with probability 1 minus P, we make a locally optimal move, right? The same move that we made in the basic local search algorithm, okay? So that's the algorithm. With probability P, you make the random walk move, and with probability 1 minus P, you make the locally optimal move. So because of the local walk, or I should say because of the random walk moves, this algorithm escapes local maximas, okay? So finally, what I want to do is I want to point out that even though I'm calling it an advanced local search algorithm, this is just one possible algorithm in a broad area of research called random walks local search algorithms. Okay? If you are interested in reading a classic paper on this topic and read about how random walk solvers have revolutionized SAT solving, you should read the paper by Selman, Kautz, and Cohen, linked on the slide. All you have to do is project the assignment x, e on each CPT in the Bayesian network to yield a probability value. And then just take the product of all these probability values. Okay, so once you do that, you get the joint probability of P of x, e. In Markov networks, this is also easy. It's easy because we need to compute P of x, e only up to a proportionality constant. And therefore, we don't have to compute the partition function or the normalization constant z. Remember that computing z is a sharply hard problem, and you'll have to use the bucket elimination algorithm over the whole network. However, for local search, right, and to be more precise, scoring function for local search, we don't have to compute z. Okay, so because we only need P of x, e to be known up to a proportionality constant. The algorithm is the same as the Bayesian network algorithm for computing P of x, e up to a constant. All you have to do is project the assignment x, e on each potential to yield a potential value, and you simply take the product of all of these potential values. Using local search for map inference is a little bit involved though. Okay, so you have to pay like close attention to this slide. The state here is an assignment of values to all map variables denoted by y. The neighborhood function are all assignments which differ from the current assignment in exactly one variable. Okay, so the same neighborhood function as before. The scoring function is a little bit complicated. The scoring function more precisely, namely the score of state S is P of y comma E, okay, where y is the assignment of values to all variables in y in your state S, and E is the evidence. You'll ask me, like, why does the scoring function create issues here? And if you're watching carefully, you'll quickly understand that in order to compute the scoring function or the score of a state S, we need to perform marginal inference, okay? Because we only have an assignment to a subset of variables, and the subset of variables being y and e. Okay, so all the so-called non-map variables, which are all variables other than y and e, we don't have an assignment to. Okay, so we'll have to marginalize out those non-map variables from the graphical model. Marginalize out or sum out those non-map variables from the graphical model. How can we do that? We can do that by using an algorithm such as bucket elimination. Okay? More precisely, if we use bucket elimination and let's say you have n non-map variables in the problem or in the graphical model, and you're given an elimination order having width w over the non-map variables, the complexity of computing the score is O of n times exponential in w plus 1 time-wise, and O of n times exponential in w space-wise. So this is the point I want to make, and I come to all the time. MAP is a really hard problem. Even local search requires that inference over the non-map variables be tractable. Okay? Otherwise, what is going to happen is that each move in your local search algorithm for map is going to be intractable. Okay? If the tree width of the graphical model over the non-map variables is very, very high. Okay? So what we need is the bucket elimination algorithm over the non-map variables to have low polynomial complexity in order to yield a practical local search scheme for solving the map problem. So to do a recap, in this lecture as well as the last lecture, we saw exact map and MAP algorithms. The exact map algorithms were based on bucket elimination and branch and bound. The branch and bound is also an anytime algorithm, and therefore it can be used as an approximation scheme. You stop the algorithm at any time and you can output the best solution found so far. We also saw an approach for bounding, and more specifically upper bounding, the MPE and MAP probabilities using an approach called mini bucket elimination. Okay? And then finally, we saw an approach called local search, which is a general approach for solving the MAP and MPE tasks. Next up, what we are going to do is we are going to look at approaches that learn graphical models from data. So until now, we have assumed that the graphical model is given to you and a particular query comes in, and we saw algorithms which perform inference over the graphical model in order to compute an answer to the query. Okay? But that's only one part of the problem. The other part of the problem when we are looking at graphical models is learning the graphical models directly from data. And those are the algorithms we are going to see for the next few classes. So the question you might have is, why do we need to learn graphical models? Okay, we need to learn graphical models because from data, I should say, because generating a graphical model by hand is not always possible. This is because if you're, let's say, interested in using a graphical model in the web domain, you might have thousands and in some cases even like millions of variables. Okay, Generating a graphical model over such a large number of variables by hand is virtually impossible. And so that's why we need automated tools in order to generate graphical models from data. So let me set up the problem, right? The learning problem for you. Okay, we always talk the problem or look at any system from what its inputs are and what its outputs are. Okay, so the input to our learning problem is a data set. Let's call the data set, which is given by this funny letter x, from x1 to xm, where m is the number of examples. Okay, and each data point is nothing but an assignment of values to all random variables in the problem. Okay, we might have missing data sometimes, wherein some value assignments are missing, but we'll look at those cases later on. One important assumption that we are going to make in order to set up our learning problem is that the examples, or also called as samples, are generated independently and identically from a distribution P star. Okay, so this is our input and these are the assumptions we are making. The output of our system is a graphical model. Let's call that graphical model M tilde, which represents a distribution. Let the distribution be called P tilde, such that the distribution is as close as possible to P star, where P star is the data generating distribution. Moreover, if you are interested in, let's say, a specific task, such as marginal inference or MPE inference or MAP inference, we want our graphical model to be adept or really good at solving this task. Okay, so we want accurate inference answers. Those are our two criteria. The first criteria is that it should be as close as possible to P star, which is the optimal answer. And the second criteria is that it should solve the task that you're interested in as accurately as possible. So one important question that we want to answer is, how do I evaluate different learning algorithms, and how do I evaluate the kind of models that the learning algorithms have output? So let's say you're given 10 different learning algorithms and each algorithm outputs a particular candidate model. How do you decide which of the candidate models or candidate probabilistic models, graphical models I should say in our case, is better or the best? Unfortunately, this turns out to be a non-trivial task because it's very hard to define or come up with a notion of best. In any case, there are certain well-established criteria in literature which work in the sense that if you are given a large number of training samples, they will always pick the correct winner. Okay, they will always pick the best algorithm or the best model. And we are going to discuss the so-called performance metrics next. So one obvious performance metric that we can use is the relative entropy or the KL distance. And we will insist on learning models P tilde such that the KL divergence between P star, which is the data generating distribution, and P tilde is minimized. The definition of the KL divergence between P star and P tilde is given on the slide. At a very high level, KL divergence is the difference between the expected value of log of P star of x with respect to P star of x and log of P tilde of x with respect to P star of x. Okay, so you are computing the expected value. The first term here is the expected value of log of P star of x with respect to P star of x, and the second term, as you can see, is the expected value of log of P tilde of x with respect to, again, P star of x. Unfortunately, One of the problems with this definition of KL divergence is that we cannot evaluate it directly. This is because it's defined over exponential number of terms, and if the model has a high tree width or it's complicated, either P star or P tilde, we won't be able to compute it. Moreover, another issue is that we don't have access to P star itself, otherwise we are done in a way, if it has a small enough tree width and if it's a compact model. Uh, we only have samples or data that is generated from P star. Okay, but the good news is that we can use a Monte Carlo estimate of the KL divergence instead of using the original value or the exact value, which is denoted by D, and the Monte Carlo estimate is denoted by D hat, and try to minimize the Monte Carlo estimate D hat. So if you remember, the way we compute Monte Carlo estimate is that we replace the expected value by sample average. Okay, so the first term in the Monte Carlo estimate of the KL divergence is the sample average over log of P star, and the second term in the Monte Carlo estimate is the sample average over log of P tilde of each sample. Okay. The good news again is that even though P star is not known, the first term is always a constant, and therefore we don't need to evaluate. The second term, which is enclosed in the brackets, is called as log likelihood of data. Okay. And since our performance metric is KL divergence and we want to minimize KL divergence, okay, KL divergence in a way is now directly proportional to negative log likelihood, and we want to minimize negative log likelihood. So this is another way of saying that we want to maximize the log likelihood. Since we are minimizing the negative log likelihood, our optimization criteria now becomes maximizing the log likelihood. Thus, from the previous slide, it is obvious that we should prefer models that have the maximum value for the log likelihood score, which is the sum over all the samples log of P tilde of that samples. Okay, this, if we maximize the likelihood, in a way what we are doing is we are likely minimizing the error, because the log or negative log likelihood is an estimate of the error. Okay, and so since we want to minimize the error, we will maximize the likelihood. Moreover, since logarithmic or logarithm, I should say, is a monotonic quantity or monotonic function, maximizing the log likelihood is the same as maximizing the original likelihood, where the original likelihood is nothing but the exponentiated of log of likelihood. Okay. So in a nutshell, the previous slide was saying that the best candidate among a set of candidate models is the one that maximizes the log likelihood of the data. In a way, this is a task-independent metric in the sense that all we care about is finding a distribution that is as close as possible to the data generating distribution. However, if you are going to use the graphical model to solve a specific task and not care about other tasks, for example, if you only care about predicting the values of certain important variables in the graphical model rather than all the variables, we can use more specific task-directed metrics. Various task-directed metrics are used in practice, and I guess like there are a plethora of them. However, what I'm going to do on this slide is describe only two such metrics, and they are one of the most popular ones. The first metric is for classification tasks. And if you don't know what a classification task is, then I'm going to define it briefly for you, but I recommend you, if you don't know what a classification task is, then I just recommend you to read a a Wikipedia article on it, or any machine learning book, the first two chapters in it. So in classification tasks, what you want to do is you want to predict the value of just one variable, which is called the class variable, or a small subset of variables. So if you're trying to predict the value of a small subset of variables, it's sometimes called as multi-label classification problem, or even a multi-class classification problem. If the single variable, let's say, takes more than one values, then it's a multi-class classification problem. But if you are trying to predict simultaneously the values of multiple variables or a small subset of variables in the graphical model, then it's a multi-label classification problem. So let me give you an example of a classification task. Suppose you are given a set of documents along with their topics at training time, and you want to predict the value of a new document at test time, right? Or the class of the new document at test time. So that's a classification task. Okay. Uh, since in the classification task you are interested in the value of just one variable, we can use more specific task-directed metrics such as classification error and Hamming loss. Okay. Classification error is defined as the fraction of examples that are misclassified. Okay, and so you want to minimize, you want to build probabilistic models such that classification error is minimized. Hamming loss is a generalization of classification error to the multi-label setting, where what we do is we count the number of variables that are misclassified. Okay, and again, you want to minimize the Hamming loss if you want to learn a good probabilistic model. A second type of situation that is often present in real-world applications is the following. Uh, we are given data on a large number of variables, but at test time, we are only interested in a subset of variables called the query variables. Okay? Namely, what we want to do is we want to answer inference queries that are defined only on a subset of the query variables. Okay? And the other variables in the model you're not interested in at all. In such situations, what we can do is we can change our objective function and try to maximize the conditional log likelihood of the data rather than maximizing the full log likelihood of the data that is defined over all the variables in the graphical model. Okay, so the conditional log likelihood is only defined over the query variables given a value assignment to the non-query variables in the graphical models, which are denoted by Z. Okay, so Y are the query variables and Z are the non-query variables. Next, what we will do is breeze through some basic machine learning definitions. We will refer to these definitions at appropriate times, and therefore I'm just going to breeze through them rather than explaining each and every definition in detail. Okay, so we will discuss them at appropriate times when we are discussing machine learning algorithms for learning graphical models from data. The first definition that I want you to be aware of is the definition of overfitting. Okay, and overfitting is defined as a state wherein the probabilistic model learns the distribution given by the training set just too well and does not generalize to unseen data that well. For example, if you're given a training set, the highest likelihood over the training data can be obtained by a distribution that assigns a probability of 1 divided by m to each training point, where m is the number of examples. Okay? And a probability of 0 to all examples that are not in the training set. Okay, so you divide all the assignments into two, one which appear in the training set and one which do not appear in the training set. Everything that does not appear in the training set has a probability of 0, and everything that appears in the training set has a probability of 1 over m. Okay, so you have a uniform distribution over the training set and 0 everywhere. Such a distribution will have the highest log likelihood score. However, that model is likely to do a poor job. Namely, it is likely to generalize poorly on unseen examples. This distribution, in fact, will have a likelihood score of 0 on the test set if there exists an example in the test set that is not present in the training set. Why? Because the probability of that example will be 0 since it's not present in the training set, and anything multiplied by a 0 is a 0. If you remember, the definition of likelihood is the product of the probability of each example in the data set. So even if one of those examples has a 0 probability, right, the whole product will equal 0. Okay, so this is a pathological case where you're doing really well on the training set, okay, because you'll have the highest possible log likelihood score, but you will generalize very poorly. So thus, and I guess like I've already explained it, perhaps this is the most important principle in machine learning, right? Generalization. What we want to do is we want models that, or I should say what we want to do is we want to learn models that perform not only well on the training set, but also well on unseen examples. Okay? And when that happens, we say that the model has generalized well. So let me give you a concrete example from the real world. Suppose you have a smart first grader who memorizes that 2 plus 2 equals 4, 3 plus 2 equals 5, and 4 plus 2 equals 6. Okay? So if the first grader just does this memorization, he will not generalize well, because if he's presented with a question, what is 5 plus 4, and says that answer does not exist in his memorized database, the student will not be able to answer the question, or the first grader will not be able to answer the question. Okay? So unless and until the first grader understands the concept of addition, he is going to not do well on unseen examples. Okay? So this is what learning is all about, generalizing. Namely, learning the underlying concept rather than just memorizing the examples. Okay? So learning kind of the main thing that the data is telling you, right? Or the main concept that the data is about, or the distribution that generated the data is about, right? Rather than overfitting on the training set. A third important concept in machine learning is bias versus variance. Without going into the details of the precise mathematical definitions of bias and variance, at a high level, bias is defined as the ability, or rather the inability of a model to represent a complicated distribution. When a probabilistic model can represent any distribution, then I will call that probabilistic model as unbiased. Okay, so it can represent everything, and such a probabilistic model has zero bias. For example, a fully connected Bayesian network, what I mean by that is it's a complete directed acyclic graph based on the chain rule, can represent any distribution. And therefore, it is an unbiased model in that its bias is zero. On the other extreme, a Bayesian network with no edges, namely all variables in the Bayesian network, we make this assumption that are independent of each other, is an extremely biased model. Why? Because it cannot represent a large number, and in fact, it cannot represent almost all distributions out there. Another example of a low bias model is a high tree width model, because it can represent many interesting distributions. And an example of a high bias model is a low tree width model. Okay, so high tree width is low bias and low tree width is high bias. In general, what we want to do is we would like our probabilistic models to have low bias so that we can represent several interesting distributions. Unfortunately, as you'll see, that this is not always possible because there is a second concept, which is that of a variance, which competes with bias. Okay, and that's why there is a bias versus variance trade-off. So let me try to define variance for you in high-level terms rather than giving you a precise mathematical definition again. So let's say, given that you have m examples, variance, what it does, it measures how a set of models, each learned optimally using a different set of m examples, okay, sampled from the same data generating distribution, differ from one another. In general, we want our models to be robust to change in the training data. Namely, we want our models to have low variance. Why do we want that? Because if they are less prone to change, they will typically generalize better. So a small perturbation in the data would not change the model a lot. A model that has a large number of parameters will have large variance. Why? Because different parameters will converge differently. Okay, and so the model will behave differently depending if it's presented with different samples. Thus, low tree width models in general will have low variance, while high tree width models in general will have high variance. Okay, so similarly, a fully connected DAG Bayesian network will have very high variance, while an independent Bayesian network with no edges will have very low variance. Okay, and now you can already see the problem, right? Because we want to minimize both bias and variance. High tree width models have low bias but high variance, and low tree width models have high bias but low variance. Okay, therefore what we actually need is a so-called sweet spot, a trade-off, namely a model that achieves the optimal balance between bias and variance. Another important concept in machine learning is that of regularization. At a high level, a learning algorithm is an optimization algorithm which searches through candidate models and finds the best one. Regularization, what it does is it biases the search towards simpler models by including a penalty term in the objective function, which penalizes complex models. For examples, we know that models having extreme probabilities are more complex because it's hard to estimate these extreme probabilities, right? As compared to models that do not have extreme probabilities. An example regularizer or an example regularization function will be a, a term which biases, or a penalty term I should say, which biases our search towards non-extreme models or simple models such that the penalty will increase the cost of the objective functions if extreme probabilities are present. And here I'm assuming that the optimization problem is a minimization problem, right? So increasing the cost when the constraint that we should not have extreme probabilities is violated will help us not select those solutions. A final concept is that of training data versus test data. In general, in real-world applications, we have access to just one data set and several learning algorithms. So how do we test which algorithms, or which algorithm I should say, among the algorithms that we have at our disposal outputs the best model? Namely, it outputs a model that generalizes well to unseen examples when we just have one data set. Another way of putting this is, how do we hallucinate these so-called unseen examples? Well, the actual answer actually turns out to be very simple. To evaluate the various candidate models, all you have to do is divide the data set into three sets: training set, validation set or holdout set, and test set. Then you learn the models using different learning algorithms using the training set. For each learning algorithm, you select the hyperparameters such as how much regularization penalty to use or how much tree width to use, for instance, using the holdout set, right? So tree width and regularization penalty here are the hyperparameters, and you choose them using the holdout set. Finally, you test each one of these candidate models output by the learning algorithms and tuned using the validation set on the test set, right? So you score the models using the test set. When you score the models using the test set, the models having, or the model I should say, having the highest score on the test set is the model that will likely generalize better. Why? Because our test set is kind of the substitute we have for these unseen examples. One thing that you should keep in mind is not to use too many learning algorithms. And I'll tell you why, right? So use maybe something like tens or in some cases hundreds of learning algorithms, but never use things like a million learning algorithms or a billion learning algorithms. And the reason is that if you do that, if you use a million algorithms or a billion algorithms, you will overfit the test set. Okay? So in a way, what happens is that the learning algorithm becomes a hyperparameter, and now you're tuning that hyperparameter on the test set. So you're going to overfit the test set. Also, never tune the hyperparameters using the test set. Again, you are overfitting the test set when you do that. In such cases, you will never generalize well to unseen examples. Okay? An alternative approach to statically dividing the data set into three sets, training, holdout set, and validation set, is to use a so-called recycling strategy called k-fold cross-validation. Here, we divide the data set into k bins and run the algorithm k times. At each iteration I, we use the ith bin as the test data and compute an average score over the k bins. The algorithm or model that yields the highest score, in this case, is the winner. Okay, so there are two strategies. One is this static division of data sets into training, holdout set, or validation set, and test set. And the second strategy is to recycle the data, and this is called as k-fold cross-validation, right? Where k is a number that is typically chosen between 5 and 10. A final point I want to make is that we will discuss learning algorithms under the following data observability scenarios. The first one is the easy case wherein we are given a data set in which each example is an assignment of values to all variables in the graphical model, right? So these such data sets are called as fully observed data set. The second case is a harder case in which we have missing values in the data. Namely, there exists training examples T in the training data such that one or more variables are unobserved in T. The final case is the hardest case, where the data set is such that some variables in the graphical model are not observed at all, right? And those variables are called as hidden variables. As you can imagine, the learning task becomes harder as we move from the fully observed data to partially observed data to graphical models that have hidden variables. So as we move from top to bottom, the learning task becomes harder. As a result, what will happen is that the learning algorithms that we'll discuss will also get more and more complicated and sophisticated as we move from top to bottom. Okay? So this concludes our discussion on machine learning concepts. It was kind of a very fast go through some machine learning concepts. And what we will do in next class is that we will look at our first learning algorithm for graphical models.